In this presentation, we will be looking at acid-base reactions of organic chemistry. Of course, as you know, acids and bases play a very important role in chemistry. And in organic chemistry, we will look at different aspects. So, in this presentation, first we will look at a definition, or the definitions of acids and bases. That's important so we can get a better concept of acids and bases so that we can apply these concepts to solving different problems. Next, we will look at an acid-base equilibrium. So this is basically a review of your chemistry from undergraduate. Next, strengths of acids. Is one acid stronger than another? Then we look at predicting the relative strengths. How can one determine if one acid is stronger than another acid? Then we will apply these concepts to organic chemistry. And we will finally look at a concept called acid catalysis for organic reactions. And these are two types: specific acid catalysis and general acid catalysis. Okay, so let's begin. Definitions. We have here the Bronsted-Lowry definitions of acids and bases. Let's see what they are. A Bronsted acid is a proton donor. Remember, a proton here is H, hydrogen. Without its electron, it's H plus. So that's a proton. So an acid is a proton donor, and a base is a proton acceptor. So let's look at these reactions here to determine the Bronsted-Lowry base or acid. So this is the reaction between a trisubstituted amine and hydrochloric acid. Of course, the name acid for hydrochloric acid kind of gives it away, but let's apply that definition. Here is a molecule in the reactant, and in the product, notice that it has an H. By the way, that should be red. Notice that it has an H. So it has accepted this proton in going from reactant to product. In going from reactant to product, HCl has given up this as a proton to form this as your product. Notice that these electrons here are bonded now to the more electronegative chlorine. So that's the chloride anion, as you know. Let's look at this one. Benzoic acid kind of gives away based on its name. So here is the hydrogen in going from a reactant here, benzoic acid, to product. This hydrogen is gone as a proton. How do we know it's gone as a proton? Because what's left behind is a pair of electrons, which would be these electrons right here. And here's sodium hydroxide, OH, in the reactant is now water in the product. So it has acquired that hydrogen as a proton, so therefore it is a proton acceptor and a base. Let's look at another definition. I'll review another definition, and that is the definition of a Lewis acid and a Lewis base. A Lewis acid now is an electron pair acceptor. Electron pair. Notice this is different from the previous Bronsted. And a Lewis base is an electron pair donor. Keyword here is electron pair, 2 electrons. So here we have the reaction between trifluoroborane and methylamine. So this is BF3 right here, where this is B. And notice here that there is a vacant p orbital, because the boron is of course sp2 hybridized. So there is a vacant p orbital in BF3. Here we have methylamine. There is an unshared pair of electrons on methylamine. So there will be a reaction where these electrons here can now bond to BF3 by going into the the vacant p orbital, I should point out, vacant p orbital of BF3 to form a product, and here is our new bond that's formed between these electrons and this vacant p orbital of BF3. So conclusion, this is our Lewis acid because it's an electron pair acceptor into the vacant p orbital, and this is our Lewis base because it's an electron pair donor giving up its electrons to form a bond as shown here. So these are the two definitions that are primarily used in chemistry. In organic chemistry, these are used quite a bit. So understanding this definition or these definitions are very important. Let us look here at equilibrium constants for acid-base reactions. So here's an acid, HA, and here's a base. And as you know from Gen Chem, there is an equilibrium between the reaction of the acid and the base to form a conjugate acid and a conjugate base as the product. So there's an equilibrium here, and that dictates the strengths of the acid. So we can calculate the equilibrium as shown here, really the concentrations of the products divided by the concentration of the reactants as shown in square brackets here. However, these reactions are typically measured in water. So as you can imagine, water here is in high concentration. So we could say it is a constant. So we can now calculate a new constant called Ka for the equilibrium acidity of an acid, in which now H2O and KEQ are constants. So the bottom line is that a large KEQ or Ka means that the acid is a strong acid, which means the equilibrium lies to the right. On the other hand, if the Ka or KEQ is small or Ka is small, that means that HA is a weak acid and the equilibrium lies to the left. These measurements are relative to water, which is also the solvent. Okay, so these measurements are relative to water. We will see later on that there are measurements that are done in other solvents such as DMSO, because water is essentially acidic at some point, but we'll get into that later on. Okay, let's look here at what's the meaning of this large KEQ or Ka. So from the equilibrium values shown here, here's the acid and here's the base. Here's a specific value, 10 to the 9th, and here is another acid and the same base because it's relative to water as a solvent and also as a base. Here is another KEQ, and notice this is much smaller, 10 to the negative 10, and this is 10 to the positive 9. So therefore HBr is a stronger acid than HCN. So that's one way of telling. Here's another way of telling using the pKa values. And these are the values that we'll use mostly in organic chemistry, pKa. You will recall that the pKa is the negative log of Ka, which of course, as you will recall, is the K acidity in water. So let's look at this. So here's the pKa of HBr, -9. And here is the pKa of HCN, 9.2. Notice that the more negative this value is, the stronger the acid, because the larger will be the Ka. So the more negative this value is, based on this equation here, this is the stronger acid compared to this acid. So that's one way of telling acid strengths, is by looking at the pKa table or getting that value, and relative to another acid which has a different value, we can tell which is stronger than the other. So here is a pKa table. That's a small one. There are tables that are much larger, which has more entries, and you can see those in your textbook. But here is a table with just a few. We have HI, so you can see it's -0.5, very strong acid. Let's look here at water. Here's water. It's an acid because its conjugate base is OH minus. The pKa is 15.7. As you can see here, it's a weak acid compared to protonated water, such as HCl. It's a very strong acid because it's now -1.7, at least compared to water. And here is methanol. And of course, we have others like acetic acid, 4.8. So again, the pKa values here give you an idea of the relative, not an idea, it gives you the relative strengths of acids compared to each other. Okay, let us look here now at the base strengths here again. And here we're looking at conjugate pairs. So here's an acid, here's the base, water, solvent, and here is the product. So what I want you to get from this overhead here is that a strong acid gives a weak conjugate base. You will see the importance of that in a minute when we determine different bases, the strengths of different bases. So strong acid gives a weak conjugate base. Okay, so you can tell that this acid is strong based on the pKa value, and its conjugate base here is weak. A weaker acid such as HCN gives a stronger conjugate base. So if you need a strong base in organic chemistry, you would consider the conjugate acid, the deprotonation of a weak conjugate acid. Let me say that again. If you need a strong base in organic chemistry, you would consider the deprotonation of a weak acid to get a strong conjugate base. Okay, so let us apply that here. Here's HCl, pKa -7. Notice -7, which means it's a strong acid. Its conjugate base here is weak. Here is ammonia. pKa of ammonia is 38, which means here we're taking off one of these hydrogens to form this conjugate base. So you can see here, this is the conjugate base here of ammonia, So you can tell this is a very strong conjugate base because this is a weak acid. I should point out here also that if you have an equilibrium like this, the value lies to the weaker conjugate acid. So here is HCl, pKa -7, reacting with water. It goes to a conjugate acid. The pKa here is -7.4. So in other words, if you mix HCl with water and equilibrium is established, the question is the equilibrium to the right or to the left? You can predict if the equilibrium is to the right or to the left based on the values of the pKa's of the acids that are involved. The equilibrium will lie in the direction of the more positive pKa. So here's -1.74 and -74. So therefore the equilibrium here lies to the right. So if you mix HCl with H2O, the equilibrium will be to the right, where you have a large concentration of H3O plus and Cl minus. Let's look at this one. If you mix ammonia with this base here, CH3O negative, K plus, let's see what should happen. This is the pKa of ammonia, 38, very positive. And this is the pKa of methanol, which is a conjugate acid of this base. So here we are comparing only pKa values. The more positive pKa value here is 38 compared to 15. So therefore the equilibrium lies to the left. So the bottom line is, if you mix here potassium amide with methanol, this proton will be deprotonated to give this as your product, and not ammonia with this to give that as a product. Same here. If you mix HCl and H2O, you will get that as a product. Okay, so summary, if you mix this base with this alcohol or this acid, you will get this as your product because the equilibrium lies in the direction of the weaker conjugate acid or the more positive pKa as shown here. So that gives you an idea of what type base to select whenever you are deprotonating an acid, so that you can get the product that you desire. Okay, so if you did not have the pKa table, is it possible to predict the relative acidity of different compounds? And yes, you can, by looking at different factors. So let's look at the factors here that affect acid and base strengths, or the acid strengths and the base strengths of the conjugate base. So here's an acid, methane, CH4, but I particularly wanted to highlight this hydrogen, one of the hydrogens here. If you should remove this hydrogen as a proton, here's a proton, what's left behind is a conjugate base. Let's look at ammonia. Removing this hydrogen as a proton, what's left behind is a conjugate base. Notice that the conjugate base has a negative charge. So whichever atom here can accommodate the negative charge the best, it will be more stable. Now nitrogen, of course, as you know from the periodic table, is more electronegative than carbon because it lies to the right. So therefore this nitrogen can accommodate this negative charge much better than this carbon accommodating this negative charge. What that means is that this conjugate base here is weaker than this conjugate base here due to the electronegativity of the atoms. As a result, this is a stronger acid than methane. Relatively speaking, ammonia is a stronger acid than methane because the conjugate base from ammonia is stabilized through electronegativity from the atom. Let's look at another factor, hybridized orbitals. So here we have methane again. It has here a CH bond. Take this hydrogen off as a proton. What's left behind is CH3 negative. Let's look at this carbon. This carbon here is sp2. Take this off as a proton. What's left behind here is an sp2 carbon that has a negative charge. Same here, sp. What you learn from general organic chemistry is that the s orbital being closer to the nucleus and more compact. Of course, as you know, the nucleus is positive, so therefore the hybridized orbital that has more s character can accommodate this negative charge much better than a carbon that has less s character. Let me state that differently. So this carbon here, which is sp3, has only 25% s characteristic. This carbon here, which is sp, has 50% s. So therefore this negative charge is better accommodated on the sp carbon compared to the sp3 carbon. So therefore this molecule here is a stronger acid than this molecule here. So in other words, here the carbon, the hydrogen that's bonded to an acetylenic carbon is more acidic than the hydrogen that's bonded to a saturated alkane. And that's based on hybridized orbitals. Let's look at another factor, resonance. Conjugate bases that have delocalized charges are more stabilized than a conjugate base that has a localized charge. So let's look at this one, phenol. Deprotonation here gives a conjugate base that has a negative charge, and this negative charge can be delocalized throughout the benzene ring as shown here. As a result, since this negative charge is being delocalized, this is very stable or relatively stable. So it's a relatively stable conjugate base, which means that this is a strong acid. Compared to cyclohexanol, which if this is taken off as a proton, what's left behind is a negative charge that's localized. If a charge is localized sitting on one atom, it's not as stable as a charge that's delocalized as here. So based on resonance, phenol is a stronger acid than cyclohexanol. Let's look at another example using resonance here. So here we have this molecule. Here's hydrogen and hydrogen. Taking off one of these hydrogens here results in this as a conjugate base. I should quickly point out that this conjugate base is aromatic because we have 6 electrons in conjugation in a cyclic system. That's aromatic, very stable. So it's not only stable due to resonance, but due to aromaticity. So therefore this molecule here is relatively speaking very acidic. I would say very acidic because it's all relative. This molecule here, taking off one of these hydrogen as a proton, gives this. This negative charge here, as you can see here, is in conjugation here, so we can draw another resonance structure here like this, but that's the only other resonance structure. So this is not as stable as this one, where the electrons can delocalize throughout the entire system. This one, however, if you take this off as a proton, what's left behind is a localized anion. So this is the least acidic, and this is the most acidic due to the aromaticity that's gained in the conjugate base. Another example of resonance here. Here's a ketone. Notice the pKa is around 20 for this one of these hydrogens here. This is called the alpha carbon, because as you know, so therefore this is the alpha hydrogen. So the acidity of alpha hydrogens of ketones are around 20. As you can see here, not very acidic, but relatively speaking, compared to other organic compounds, it is fairly acidic. We can use KOH to remove this hydrogen to get here a base, and it is resonance stabilized, as we can see here. So this is the conjugate base of this acid here, and is resonance stabilized since we have removed one of these protons here, hydrogen as a proton. This is a relatively strong acid, relatively speaking. Okay, let's look at another aspect, polarizability or atom size. Let's look at this acid, HI. Its reaction with a base gives an equilibrium constant to give the conjugate acid of this base. So this base gives this conjugate acid here. This acid here gives that conjugate base. But we're concentrating now on HI because this is typically the solvent. So HI gives a conjugate base. Let's see if it is stable or not stable compared to another acid, HCl. This gives a conjugate base here, Cl minus. So out of these two anions, which is more stable? If you can determine which is more stable or weak, we can determine which is a stronger conjugate acid here. Looking at the periodic table, I is larger than chlorine because it's further down a column. So this is much larger. If it's larger, it's more polarizable, which means it can accommodate the negative charge here much better than Cl. As a result, this is stable and weak conjugate base because of its stability. So therefore HI is a stronger acid than HCl, just based on polarizability. Let's look at another factor, inductive effect or induction. That's based on the electronegativity of atoms that are in close regions of the conjugate base. So let's look at acetic acid here. This is the conjugate base. So relative to this conjugate base, let us look at electronegative atoms that are bonded to it or close by to this negative charge here. You can see here, let's go to the extremes. Fluorine, being the most electronegative atom, can in fact stabilize this negative charge here by induction based on its electronegativity. It can pull these electrons through the sigma bonds, hence stabilizing it, compared to hydrogen. So this is more stable, hence this is a stronger acid compared to this base, conjugate base, which does not have an electronegative atom in close proximity to this negative charge here. So hence this is a weaker acid. So this is a weaker acid compared to this acid, which is a stronger acid. That's based on the inductive effect of electronegative atoms that are bonded in close proximity to the negative charge of the conjugate base. Let's look at another aspect here of the same induction. As you can imagine, if you should put a electronegative atom close to the negative charge of the conjugate base, it would be a stronger acid than putting it further. So this fluorine is further from the reaction site than this one. So therefore this is a stronger acid than this one. Same here. Substituted benzoic acid, this fluorine is way over here and this fluorine is much closer. So therefore this is a stronger acid compared to this acid. So again, this is based on the inductive effect of electronegative atoms that are in close proximity to the reaction site or the acid-base reaction site of acids. Let's look at another aspect here, the isotope effect, which is what we did in an earlier lecture. So you know that the OD bond has a lower 0 point energy compared to the OH bond. Now remember, the 0 point energy is that minimum energy for the vibration of these bonds. So therefore, the equilibrium of D3O plus will lie further to the right compared to H3O plus, owing to the stability of the 0 point energy stability of D2O. So looking at it differently, here is D3O plus, an acid, because we have here very stable OD, or should I say 0 point energy bonds here. This equilibrium will lie to the right compared to H3O plus, where these 0 point energies here are much higher. Well, I shouldn't say much higher, but higher, relatively speaking. So therefore this D3O plus is a stronger acid because the equilibrium lies more to the right, giving up more D plus. Remember, D plus here is an isotope of hydrogen. This H3O plus here does not lie as far to the right, less H plus compared to D plus because of the higher 0 point energy of the OH. So conclusion, D3O plus is a stronger acid than H3O plus. Let's look at solvation effect as it affects acid strength. So due to polarizability effect from the ethyl groups shown in the molecule below, triethylammonium ion is a weaker conjugate acid compared to diethyl. It's in the gas phase. Keyword here is in the gas phase. So let's look at what we're talking about here. So we have a nitrogen that's positively charged as an acid. In the reaction, it gives up the H as a proton to give a neutral molecule. Remember, neutral molecules are stable based on just inherent effect of it being neutral. So since this is positive, it has 3 ethyl groups around it. Ethyl groups are not large, but large enough to be polarizable, so it can be polarized to stabilize this positive charge. And that's what I try to indicate here. This ethyl group can be polarized, so we have a partial negative at one end and a partial positive at the other end. Since this partial negative is close to this positive here, this group here can stabilize this positive charge. Same here, same here. So we have 3 polarizable groups that can stabilize this positive charge. Hence, this is a relatively stable conjugate acid here, which means that this ethylamine, triethylamine, is a strong base in the gas phase. Notice again, in the gas phase, compared to diethylamine, where we only have 2 ethyl groups to stabilize this positive charge here by polarizability effect, compared to 3. So therefore this is not as stabilized as this one because it only has 2 groups. So therefore this is a weaker base in forming this stronger conjugate acid in the gas phase. Let us look here at in solution, or in water to be specific. So due to solvation effects, this has a greater effect on stability of a charge compared to polarizability effect. So in solution, you will have to consider solvation effects. So let's look here. So we have here diethylamine, diethylammonium salt. It has the potential to now hydrogen bond here to 2 water molecules. Here are the hydrogen bonds by so it's very much solvated. The ethyl groups here will provide polarizability effect, but not nearly as much as stability from solvation. So as a result, this is more stable in solution, in water, compared to this triethylamine ammonium salt, because it only has 1 hydrogen to form that solvation. Notice this is the reverse of what's observed in the gas phase, and this reversal is due to solvation having a great effect compared to polarizability. I should point out here that a similar observation is made for substituted alcohols, where tert-butanol is a stronger acid in the gas phase because it goes to a very stable conjugate base, which is stabilized by polarizability effect compared to that in solution. So let's apply some of this knowledge here. For the next few slides, we'll apply the knowledge that we've gained. So again, if you have cyclohexanol and you would want to remove this proton here, you remember we said earlier that cyclohexanol is not a very acidic molecule because it forms a conjugate base here with a localized charge. So you have to use a strong enough base to remove this hydrogen as a proton. So this has a pKa value of 15. So let's see how we can get this to go to the right so we can get this as the product, if that's what we need. Sometimes we need that as a reactant for different reactions in organic chemistry. So looking at this here, H2 or HH, it has a pKa value of 35. In other words, if you take off the H plus, its conjugate base would be H minus. Very strong base. And here it is, H minus, so that's Na plus and H minus, sodium hydride. So sodium hydride as a base will drive this equilibrium to the right, because, as I mentioned earlier, the equilibrium will lie in the direction of the more positive pKa values. So you'll have to find the pKa values of the acids. So you'll have to identify the acids here in this equilibrium, determine the pKa values of those acids, and the equilibrium will lie in favor of the more positive pKa. Notice the larger the difference, the more the equilibrium will be driven to the direction of the more positive pKa. So this reaction here, because this difference here is pretty large, it's driven to the right as shown here. Let's look at this one. Here's the acidic hydrogen, or the hydrogen that will be taken off as a proton. It has a pKa value of around 19. It's an ester. So what base can be selected to pull this equilibrium to the right if this is what we need? Here we can consider methanol. It has a pKa value of 16, which means that its conjugate base is fairly strong. So let's see, so here's a conjugate base of methanol, and here is plus 19 and plus 16. So as you can see here, the more positive is over here. So this equilibrium here is really an equilibrium. We have a mixture of all of these in solution here. The mixture of all of these in solution. So if you really want to pull this off and drive this to the right, you may want to consider using a base such as sodium hydride. But what you'll discover is that a lot of times for the reaction that's needed, you just need an equilibrium to generate this, if this is what you need, so it can react in another reaction. So the bottom line for this slide is you can determine what base is needed to pull off hydrogens as protons to shift the equilibrium to the right to generate the anion or the conjugate base that's needed. Let's look at this one. This is another example, cyclohexanol, pKa value around 19. If you want this as your base, you want equilibrium driven to the right here. Let's see what's a good base. Let's consider this as an acid, because if we remove this hydrogen, we get a conjugate base. Since the pKa of diisopropylamine is around 36, its conjugate base, which is right here, is pretty strong. Very strong, because a weak conjugate acid gives a strong conjugate base. So this is LDA, lithium diisopropylamide, a strong base, and as you know, it's also very bulky base because of these two isopropyl groups. So it's a strong and bulky base. It can remove one of these hydrogens here as a proton. So it can take off this hydrogen here as a proton, which is over here, to give this conjugate base here, which is the enolate. Again, because of the difference in pKa values, this is very positive, so the equilibrium is driven to the right, so you're guaranteed in this case to get a large percentage of your enolate, which is a conjugate base. One thing I should point out here though, this is the solvent, tetrahydrofuran. You may recall that tetrahydrofuran here is this. It has no hydrogen that's bonded to an electronegative atom. All the hydrogens are here bonded to carbon. So therefore this is described as a aprotic solvent. Aprotic, which means a solvent that does not have a hydrogen that's bonded to an electronegative atom, which makes it a protic solvent. So this is an aprotic solvent. A solvent such as water, as you can imagine, is a protic solvent because this hydrogen is bonded to an electronegative atom. Methanol, as you can imagine, is also a protic solvent because this hydrogen is bonded to an electronegative atom. So a strong base such as LDA will pull that off as a proton. So you'll have to be careful here in your selection of solvents for these reactions. Here are just some examples of some strong conjugate bases based on the strengths of the conjugate acid. Organomagnesium. The conjugate acid, as you can imagine, is CH3. Would be ethane, weak acid. So therefore this is a strong conjugate base. Sodium amide, we've seen this before. The conjugate acid of sodium amide is ammonia, very weak. Sodium hydride, we've seen it up here on the previous slide. The conjugate acid here of this sodium hydride, or the hydride, is H2, very weak acid, so a strong conjugate base. Potassium methoxide here. So the conjugate acid of this methoxide anion is actually methanol. So that's a weak acid, so therefore this is a fairly strong conjugate base. Okay, let's conclude by looking at an application of acids in organic chemistry. As we know, a large percentage of organic reactions are catalyzed by acids. For example, the reaction of ketones and aldehydes with water or alcohols to form hydrates or ketols are catalyzed by acid. So just recall your chemistry where you react an aldehyde with water to form a hydrate. It's acid catalyzed. We have two types of catalysis here. One is called the specific acid catalysis, and the other one is the general acid catalysis. So let's define these catalysis and then let's apply it to a reaction. So for a specific acid catalysis, the proton has been fully transferred before the rate determining step. Key here is rate determining step. That's the slowest step of the reaction, which dictates the overall rate of the reaction. So for a specific acid catalyzed reaction, the proton is transferred before the rate determining step. So here we have an illustration of this. So we have here's the proton. It's transferred to the substrate in an equilibrium typically to form this. And in the rate determining step, this falls apart or dissociates to give the final product. For the general acid catalysis, the proton is transferred during the rate determining step. So here's the substrate, here is the proton, which typically is part of the solvent, H3O plus, for example. And this is done in the rate determining step to form here a protonated substrate, and then in a fast step the protonated substrate gives the product. So then again, these are the concepts, these are the definitions. Specific acid catalysis as shown here, and general acid catalysis as illustrated here. Now let's apply this concept or these concepts. So let's look first at the specific acid catalysis. So here's an aldehyde. methoxybenzaldehyde. In the first step here, the proton is transferred to give this protonated species. That's a fast step. That's an equilibrium. Fast step. Of course, you can draw resonance here to put a positive charge on this carbon. Once this is formed, now comes the water, the nucleophile, to react here in the rate determining step to give the product, which is the hydrate. So the reaction is the aldehyde going to the hydrate, which is the reaction of water in the presence of an acid. For this reaction, as shown here, it is specific acid catalyzed, where the proton is transferred in the fast step and the water reacts in the rate determining step. You may say, how can we know that? So let's look at deuterium, which we said earlier is a stronger acid than proton. So if we were to change this to D+, since it's a stronger acid, this equilibrium will lie more to the right, which means we have more of this protonated species. So this concentration is higher if it's D2, if it's D+, which means that we have more concentration here, or higher concentration here if it's D compared to H. So therefore this rate determining step is faster if it's done in D+. So let me just go over that again for emphasis. So if we use D+ here as the acid, the equilibrium here would be to the right, a lot more of this species here, where this is D and this is D. If this is a high concentration with D, which means that now the reaction here, which is the rate determining step, would be faster because we have more concentration or higher concentration of this species with deuterium compared to this species with hydrogen, which would be slower. So bottom line is, if this reaction were done in D+, the RDS would be faster compared to doing this reaction in H+. So that's way off determining a specific acid catalyzed reaction. Let's look at a general acid catalyzed reaction here. So let us look here at this reaction. So in this step, it's the rate determining step where the proton and the nucleophile reacts in the rate determining step to get this intermediate protonated substrate. Then in a fast step, it breaks apart to give the hydrate. Same reaction here, where this aldehyde goes to the hydrate here. As you will see, the group that's bonded here is different. This is the nitro group, which is pulling electrons, making this more positive. That's why this reaction just goes as one. The other one was the methoxy, which stabilized that carbocation. So it makes a difference. So here again, this is general acid catalyzed, where in the rate determining step, these go as one. And then in the fast step, this breaks apart. So if we were to use D+, since this is the rate determining step here, where D+ and H+ are just an acid, it will not affect the rate determining step. So again, if this were D+, even though it's a stronger acid, it's still protonating in the first step. Still a protonation in the first step here to give the rate determining step, and hence there's no effect. So there should not be an overall effect here. Just to refresh your memory here, since this is the rate determining step, you notice that this carbon is sp2 and this is sp3. So if we were to use here deuterium and deuterium here, you should see here a kinetic isotope effect. It should be also observed in the specific rate catalysis for that type of reaction. So again, this is where we're going with this course, is to try to put all the tools together to analyze different reactions. So that's the end of this lecture for acid-base chemistry. So once again, just to recap, acids and bases are very useful in chemistry, and in particular organic chemistry, and it's to maximize on the benefits of acids and bases. We need to know the strengths of these acids and bases. We can determine that from the pKa table, but if it's not given, we can predict it based on different factors such as electronegativity of the atom, inductive effect, resonance, etc. So you should be able to do that. And lastly, you should be able to utilize that knowledge to determine which acid or which base can be used to generate the conjugate acid or base that's needed for your reactions. Okay, so continue to study hard, and our next lecture will be on substitution reaction, which I will get out shortly. Okay, bye.